Okay, so for my birthday this past year, I got a cookbook from my sister, which is this very nice book, Salt, Fat, Acid, Heat. I don't know. There's also a Netflix series which I recommend. I really enjoyed watching this. So I was reading this book, and it struck me that it was like a really beautiful discrete math problem. So I'm just going to read you this paragraph. So it's about how to make like flaky pastry. Okay, so the flakiest pastries are made with laminated doughs. Picture your flakes on your plate or shirt after you've eaten a classic puff pastry, such as cheese straw, palmier, or strudel. It's a mess, a pile of gorgeous glassy shards. To achieve this texture, a flaky dough is wrapped around a large slab of butter. The dough and butter sandwich is rolled out and then folded back upon itself in a process called a turn. Classic puff pastry, when turned 6 times, will have precisely 730 layers of dough separated by 729 layers of butter. Okay, so here's a question. Why 730? How to get that count? And actually, I mean, like I have a friend who's a baker, and I was trying to get this number and I couldn't get it. I mean, I kept getting different answers for 6 turns because I didn't know how it worked. So she texted me a photograph of how to fold dough. And here's how it works. So here's the question: why 730 layers of dough? And you can also ask another question about like, okay, how to calculate the number. I mean, like, what if I did it with 18 folds? Or what if I did it with 3 folds? What would the number of layers of dough be? So the way it works, and this is why I was getting the wrong answer, is because you don't fold it in half. You fold it in thirds. You do 2 folds each time you do a turn. Okay, so this is called a book fold. And this is a standard thing that people do when they make things like croissants or millefeuille or whatever. So I take the right-hand side, I fold it down, and then I fold the left-hand side on top. So I start with 2 layers of dough and 1 layer of butter. I mean, I take my slab of butter, I wrap it in dough. That gives me a layer of dough on top and a layer of dough on bottom with butter in between. So after I've done that fold once, how many layers of dough do I get? Well, it's interesting. You might think that everything triples because I fold and I fold. So I started with 1 layer and I got 3. But the layer of dough on top touches a layer of dough on top of the part that it's folded on top of, right? Like 2 layers of dough end up touching, and those get smushed into just 1 layer of dough. So if I look here, let me switch to brown, like this part here and this part here, it's 2 layers of dough that get smushed together to form 1 layer of dough. So in this picture, after 1 fold, I have 3 layers of dough, or sorry, 4 layers of dough, 1, 2, 3, 4, and 3 layers of butter. So let's think about the sequence of layers of dough that I have after n turns. So in the first example, when I've done no turns, how many layers of dough do I have? I have 2. So at the outset, I start with 2 layers of dough. Then if I fold once, the part on top here and the part on top here get identified. They get smushed. Likewise, when I do this fold, there are 2 layers of dough that become 1. So here I have 2 layers of dough that become 1. Here I have 2 layers of dough that become 1. So I multiply by 3 and I subtract 2 because I've overcounted twice. Because two layers of dough get identified here and 2 layers of dough get identified here. So I multiply by 3 and I subtract 2. Does that make sense? So this is what we saw in this first case. So if I just didn't think about this identification, I would have 6 layers. I would have 1 here and 2 here, 2 here and 1 here. That's 6. But I double counted this and I double counted this, so I subtract 2. Okay, so this gives me my general rule. Now, using this general rule, I can calculate. So D0 is 2, D1 is 4, D2 is what? Well, 4 times 3 minus 1, or sorry, 4 times 3 minus 2 is 10. 10 times 3 minus 2 is 28. 28 times 3 minus 2 is 82. 82 times 3 minus 2 is 244. And D6 is 244 times 3 minus 2, which is 730. That's the answer. Okay, cool. So we got it. But notice how unfun it is to calculate this number. In order to calculate D6, what did we have to do? We had to know D0 in order to calculate D1, because D1 was given to us by an expression involving D0. We were told D1 is 3 times D0 minus 2. And in order to get D2, we needed to know D1. And in order to get D3, we needed to know D2. So if I wanted to calculate D6, I needed to calculate D5 and D4 and D3 and D2 and D1. And okay, for 6, that's not such a big deal. But imagine that I wanted to calculate D72. Now, if I want to calculate D72, using this procedure, I would need to calculate D1 through 71. And then once I knew D71, I could multiply it by 3, subtract 2, and I would have D72. That's a lot of work. What would be much better is if I just had a formula that I could plug into I could plug into, and it would output the right answer. So this kind of formula is what we'll call a recurrence relation. It's where you're told how to calculate dn plus 1 in terms of some of the numbers that came before. And what we're often interested in is ways of calculating the value dn, for example, without needing to calculate any of the other things. It's like much simpler. Like, it's better if you can calculate things directly instead of having to do 18 million other procedures before you can get there. So let's think now. We figured out this recurrence relation here, this general rule that says dn plus 1 is equal to 3 dn minus 2. Is there a different way of calculating it so that we don't need to talk about the other values of the sequence in order to calculate a value of the sequence? So in this case, there is one, which is, oh no, my screen share has frozen. Let me stop share, and we'll start again. Okay, so now let's think, instead of thinking about the layers of dough, let's think about the layers of butter. Okay, so Bn is going to be the layers of butter that I have after n turns. So when I began, what did I start with? I started with a slab of butter that was surrounded by dough. So that's one layer of butter. It's just my slab of butter. And then after I folded it, I got 3 layers. And after I folded that again, I get 9 layers, and so on and so forth. Because both sides of the butter are covered in dough, when I fold, I never squish 2 layers of butter together. So I really do just triple. So what is b to the n? It's just a power of 3, right? So I start with 3 to the 0, then I get 3 to the 1, and then I get 3 to the 2, and so on and so forth. So if I want to calculate d to the n, I could just try to do it in terms of b to the n. So let's think about this. If I go back to the picture here, what is the relationship between layers of butter and layers of dough? Well, notice that if I start, I have dough, and then I have butter, and then I have dough, and then I have butter, and then I have dough, and then I have butter, and then when I get to the bottom, I have one more layer of dough than I have butter. So the number of layers of dough is just the number of layers of butter plus 1. Every layer of butter has a layer of dough on 2 sides, the top and the bottom. So every layer of butter has a unique layer of dough on top, but then there's the bottom layer of dough, which has no layer of butter below it. Right, so butter equals, well, so yeah, so the butter equals dough minus 1. So this gives us the following relation, which is the layers of dough is equal to the layers of butter plus 1. And we know an explicit formula for Bn, which is 3n plus 1. So I think this is kind of cool. So you have this iterative procedure to count the layers of dough. You take the number of layers of dough, you fold, and then you subtract 2. You multiply by 3, you subtract 2, you multiply by 3, you subtract 2. That tells you how to calculate dn plus 1 in terms of dn. But if we think more cleverly about this problem, then we can instead write it in closed form as 3n plus 1. And notice that this does not, let me do it this way. This does not reference D0, sorry, D1 through Dn. Okay, it just gives you some function in terms of numbers. So now what we'll do is we'll talk about recurrence relations. In the abstract. So here's the definition. So a recurrence relation for a sequence an is an equation that relates an plus 1 to its predecessors, a1 through an. Okay, so before our example was like dn plus 1 is equal to 3 dn minus 2, okay, i.e. And we have initial conditions. So initial conditions for a recurrence relation are equalities specifying the value of sum of the first terms in the sequence. Okay. So this is the definition of initial conditions. All right. So what is the idea here? The idea here is like a recurrence relation is in some sense the idea of constructing a sequence by induction. So induction, if you recall, we introduced to talk about how to prove things by the natural numbers, somehow going step by step. So I want to prove something about all natural numbers. Well, I can break this up into 2 steps. So first I can prove P1, and I can prove that wherever Pn is true, Pn plus 1 is true. So I can think about proving, say, P16 as something that I do in 15 steps. I prove P1, and from P1 I prove P2, and from P2 I prove P3, and from P3 I prove P4, all the way up to P16. So there are 16 steps here. So the idea is you might try to construct a sequence also step by step. So I'm given some initial condition, like what A1 is equal to, and I'm told how from A1 to calculate the value of A2. And I'm told how from A2 to calculate the value of A3. And this gives me a way of constructing step by step a sequence, also throughout all the natural numbers. And oftentimes we're given a recurrence relation like this, and then we want to prove that the equation can be described by some kind of closed form expression that doesn't refer to the previous values, so that you don't have to go through the hassle of calculating A1 through A million in order to figure out what A million and 1 looks like. Okay, so so for those of you that are computer science people, this is a familiar idea. It's exactly just constructing a sequence by recursion. You know, if you have something like a if-then clause, you know, you can do it step by step. This happens all the time in computer science, but also if you're more of like a physics person, then you can think about recurrence relations as the sort of discrete analog of a differential equation. So if you have a differential equation like x is equal to the derivative of x, you're saying how to define a function in terms of its rate of change. And that's sort of like what you see here. So what you're saying is I'm sort of told essentially how to shift from n to n plus 1. It's a little bit like saying what the rate of change is at a given point. And so once I know a value, I can start describing its behavior. And actually, there are a lot of interesting analogies between difference equations or recurrence relations, as they're sometimes called, and differential equations. So this is in some sense an analog also of what you see in physics when you do differential equations. Okay, so let's just start by thinking about some examples. So I think like the most common example is something that we all learn, I don't know, in elementary school, which is the Fibonacci sequence. So the Fibonacci sequence starts with the initial conditions. A1 is 1, A2 is 1, and if I'm given some number n, then I know that an plus 2 is equal to a n plus 1 plus a n. So this is true for all natural numbers. So this equation here is our recurrence relation. And this pair of equalities are our initial conditions. Okay,